Hi and welcome to this segment where we're going to look at subspaces. Before we continue, I would like to make a correction in the previous video. Okay, so in the previous video we were trying to look at an example or we are trying to show that the set of matrices, okay, of size, the set of real valued matrices of order m by n is a vector space over R. Okay, now when it came to M5 here, I realized I mentioned this as the identity, which is wrong. This is scalar multiplication, okay? Because we say this is A, this is vector addition, okay? This is vector addition, and then what we are trying to show down here is scalar multiplication, okay? This is a what? Scalar multiplication. In other words, what we are trying to say is that, of course, when you multiply 1 with the matrix, the scalar 1, okay, not the identity matrix, okay, it is the scalar 1, because if I say it is the identity matrix, then it would be as if I am dealing with a vector and a vector multiplication, okay, but this is scalar multiplication, so I have the scalar 1 multiplied with the vector, so it is 1, that's 1 the scalar multiplied times the vector, in this case, which is this Rm by n. It will still give us an Rm by n and exactly the same matrix. Okay, so I am sorry about that, and maybe we can move on now to the section for today. Now we would like to start by saying that maybe I could change this and use the proper color here. So what do we say? We would say that let S be a non-empty subset. Let S be a non-empty subset of a vector space V, okay, over F. In other words, S is a subset of this vector space V. Remember, we said that V is a vector space over F if it satisfies the properties of scalar addition, that was A1 up to A5, and scalar, this is vector addition, and scalar multiplication, that was M1 up to M5. Were they 5? Yes, they were 5. Okay, so we are saying let S be a non-empty subset of a vector space V over F, okay, written as that. So we say that if S is also a vector space, if S is also a vector space over F, in other words, if the same if these axioms or these properties A1 up to A5 and M1 up to M5 are also satisfied, okay, you under the same addition and scalar multiplication, then S, okay, then S is said to be a subspace of V. In other words, 1, S is non-empty subset of a vector space V, and this vector space V is over F. So if S is also a vector space over F, then S is a subspace of V. If S is also a vector space over F under the same, okay, maybe here you can include under the same vector addition and scalar multiplication, under the same vector addition and scalar multiplication, then S is said to be a subspace of V. Okay, now in dealing with this, actually, in trying to show that S is also a subspace of V, the theory says that it is actually enough to check for just A1 and M1, okay, that you can just, we won't go in so much into detail, but as long as you can simply check for M1, remember M1 says that this for every x and what and y taken from z. Okay, and then what does M1 say? M1 is scalar multiplication, that alpha x is also taken from z for alpha taken from maybe if we are using the same idea here, if s for is taken from v, okay, x and y taken from v, and then this is that if alpha is taken from f and x is taken from v. Okay, now yeah, it's enough. They say to show that it is a subspace, that to show that S is a subspace of V, it is simply enough to check that A1 and M1 are verified. Okay, but we won't go so much into detail, but the text gives examples. I mean, it gives some more detail why it is just enough, while the rest follow from A1 and M1. So now our idea here was just to give that definition and then move on to what we call spanning sets. Okay, so this section is going to have quite a number of definitions. You bear with us, there's no other simpler way you can do this without defining some of these. So we say that for a set of vectors S, which is given by maybe v1, v2 and so on up to vn, okay, we are going to say that the span of S is going to be, okay, is defined as a linear combination of those vectors which are in S. Okay, so this here, okay, the span of S is simply defined as a linear combination of those vectors in what? In S, okay? And we can write, and then we can say that V is equal to the span of S if every vector in V can be written as a linear combination of vectors in S. Okay, so we will say that V, okay, is equal to the span of V is the span of S if, in other words, the vector V spans the set S if every vector in V, okay, can be written as a linear combination of vectors in what? In S. Okay, we shall look at an example here. Let us look at an example here to try to drive this point home. So for example, we have the set S, which consists of the vectors 1, 1 and 2, 1. Okay, we are going to say that this one here spans, okay, the line y equals to x in R2. Okay, so now this is what we are going to say, that this set here spans the line y equals to x in R2 because every vector in here, okay, can be written as a linear combination of the vectors in there. For example, you can choose of any vectors in R2 which satisfy the line y is equals to x. Maybe if x is 0, y is 0. If this is negative 1, this is negative 1. Okay, if this is 3, this is 3. If this is 9, this is 9. In other words, all of these in R2 are taken from y is equals to x in R2. Okay, in other words, all these vectors here can be written as a linear combination of their vectors in S. Do you want to see that? This one here, 0, 0, can be written as a linear combination of the vectors in S. All you need to do is multiply everything by 0. Okay? This one here, negative 1, 1, can be written as a linear combination of the vectors in S. We are simply going to say have that and then plus 0, 2, 2. Okay? The other vector 3, 3 can be written as a linear combination of that, of the vectors in S. The other 9, 9 can also be written as a linear combination. How can we write it? We can multiply this by 4 and then we add this one here. In other words, any vector here in R2 satisfying the line y equals to x can be written as a linear combination of these vectors here. So we say that the set S equals to, given by all these two, given by the set S which contains these two vectors here, spans this line here in R2, because every vector in here can be written as a linear combination of the vectors in S. Okay, I hope it makes some sense with this here. We have a set S which contains these vectors here. Okay, in that example here we had 1, 1 and 2, 2. So we are saying that the set S spans the vector V, okay, because every vector in V can be written as a linear combination of the vectors in S. In other words, every vector in V which we chose, okay, which satisfied this, could be written as a linear combination of these vectors. I hope it is not ambiguous, but you can try to think about it. Okay, take some time and think about it. I hope it will make some sense. Maybe we can look at another example here. What is this other example here? Let's see. We have the set given by the vectors 1, 0, 0, okay, and then we have E2 given by 0, 1, 0, and then we have E3 which is given by 0, 0, 1. So we are saying that this set here spans R3. So when we say that this set here, maybe let us use the usual. This space, I mean this set here S equals to, given by this, spans R3. It means that every vector in R3, okay, can be written as a linear combination of the vectors in S. The vector S given by this spans R3, means every vector in R3 can be written as a linear combination of the vectors in S. So you can think about any vectors in R3 really, even if you think about the simplest one, okay, which is taken from R3, we know it can be written as a linear combination of these vectors. In fact, it is just that. Okay, that is the simplest case. So any other, whether it is 5, whether it is 0, and then maybe negative 1, this is still taken from R3. It can be written as 5 times 1, 0, 0, plus 0 times 0, 1, 0, then plus negative 1 times 0, 0, 1. In other words, every vector you can think of from R3 can be written as a linear combination of these. Okay, later on we shall see that these vectors here form what we call the basis. We shall later on explain the basis. In fact, these are the unit vectors here, the unit vectors here, these unit vectors in R3. Okay, these are the unit vectors, unit vectors, unit vectors, in R3. Okay, so that is the meaning of a span. Once again, I go back and say that V, okay, is spanned by the set S if every vector in V can be written as a linear combination of the vector in S. Okay, so the span of S is just a linear combination of all the vectors in V. So thank you, and we'll meet in the next video.